All right, let's go.
Number 10. Solar flares, the electromagnetic ambush. The sun is not stable. It never has been. Right now, the surface of the sun is a churning, violent mess of magnetic field lines twisting around each other, building tension for weeks or months at a time. When those field lines finally snap and reconnect, they release energy, enormous amounts of energy, in seconds. That's a solar flare. The most powerful ones, X-class flares, release energy equivalent to billions of nuclear bombs simultaneously. The radiation travels at the speed of light. It hits Earth 8 minutes after leaving the sun. No warning, no preparation time, just arrival. In 1989, a solar flare knocked out power across the entire province of Quebec in 90 seconds. 6 million people. No electricity for 9 hours. That was a moderate event. The Carrington event of 1859 was the largest solar flare in recorded history. Telegraph wires caught fire across Europe and North America. Operators received electric shocks. Some telegraph systems continued operating even after being disconnected from their power sources, running purely on the induced current from the flare. Now imagine that hitting our modern infrastructure. Every satellite disabled, every power grid fried, every internet cable with induced current burning through its circuitry. The entire global financial system, which runs on electronics, gone. GPS gone, communications gone. We are not prepared for this, and it will happen again. Not if, when. Number 9. Coronal mass ejections, the billion-ton plasma cannonball. A solar flare is radiation, fast, invisible, unstoppable. A coronal mass ejection is different. It's physical. When the sun's magnetic field erupts, it can hurl an actual blob of plasma, billions of tons of charged particles, directly into space at millions of kilometers per hour. These are coronal mass ejections, and if one hits Earth directly, it makes a solar flare look gentle. The plasma interacts with Earth's magnetic field and compresses it. On the night side, the magnetic field gets stretched so violently it snaps, releasing stored energy directly into the upper atmosphere. This drives currents through anything conductive on the ground. Power lines, pipelines, railway tracks, anything long and metal becomes a conductor for millions of amps of induced current. Transformers explode. The transformers that run the power grid, the enormous ones that take 18 months to manufacture and cannot be quickly replaced, are shown destroyed simultaneously across entire continents. In the worst-case scenario, a direct hit from a major CME could leave large portions of the developed world without electricity for months to years, not days, years. Modern civilization runs on electricity. Food distribution, water treatment, hospitals, heating, cooling, all of it collapses without power within weeks. The near miss of 2012 is something most people have never heard of. A CME of Carrington-level magnitude passed through Earth's orbital path. We missed it by 9 days. 9 days. If Earth had been slightly earlier in its orbit, we would have taken a direct hit. 9 days. Number 8. Ultraviolet radiation, the slow burn already happening. The sun kills slowly too, not just dramatically. Ultraviolet radiation, specifically UVB and UVC, is constantly streaming from the sun. The only thing standing between that radiation and every living thing on this planet is a layer of ozone in the stratosphere, roughly 3 millimeters thick if compressed to sea level pressure. 3 millimeters. UV radiation at full unfiltered strength destroys DNA directly. It breaks the molecular bonds in the double helix, causing mutations, errors, and cellular death. Without the ozone layer, the surface of Earth would be sterilized. Not just hostile to humans, sterilized. The base of the food chain, phytoplankton, and surface plants would die first, then everything above them. We almost learned this the hard way. In the 1970s and 80s, the ozone layer was thinning rapidly from chlorofluorocarbon emissions. The ozone hole over Antarctica was expanding. Scientists calculated the trajectory and found it catastrophic. The Montreal Protocol of 1987 banned the chemicals. The ozone layer is slowly recovering. But here's what most people don't know. The sun's UV output is not constant. During solar maximum, the peak of the 11-year solar cycle, UV output increases significantly. And over billions of years, the sun has been getting brighter, slowly, about 1% brighter every 100 million years. That 1% has been accumulating for 4.6 billion years. Number 7. The sun's increasing luminosity. The slow death, already in progress. Here's a threat that doesn't make headlines because it operates on timescales that feel irrelevant, but it isn't. The sun gets brighter over time. This is not controversial. It is a direct consequence of the physics of stellar evolution. As the sun fuses hydrogen into helium, the core gets denser, the pressure increases, and the fusion rate slowly climbs. The sun today is approximately 30% brighter than it was when Earth formed 4.6 billion years ago. In about 1 billion years, it will be 10% brighter than it is now. 10% doesn't sound like much, but Earth's climate is extraordinarily sensitive. A 10% increase in solar output is enough to trigger a runaway greenhouse effect. The oceans begin evaporating. Water vapor, itself a greenhouse gas, accelerates the warming. The process becomes self-sustaining, unstoppable. The oceans boil away. The atmosphere becomes a thick, humid, crushing blanket of water vapor and CR2. Surface temperatures climb past 100 degrees, then 200, then higher. Earth becomes Venus. Not in 5 billion years when the sun expands, in 1 billion years, just from slowly increasing brightness. Every species alive today, every ecosystem, every ocean, every forest, operating on borrowed time. The clock is running. We just can't see the hands moving. Number 6. Solar energetic particles. The invisible bullets. When major solar flares and CMEs occur, they don't just release radiation and plasma, they also accelerate particles, protons and electrons, to near light speed and fire them directly into space. These are solar energetic particles, and they are essentially a natural particle accelerator aimed at Earth. At sea level, Earth's atmosphere and magnetic field absorbs most of them, but at altitude, the situation changes dramatically. Astronauts on the International Space Station during a major solar particle event receive radiation doses equivalent to hundreds of chest X-rays in minutes. During a large event, the risk of radiation sickness becomes real. During an extreme event, fatal doses are possible. But it gets more personal than astronauts. Commercial airline passengers flying polar routes, the Great Circle routes from North America to Europe and Asia, fly at altitudes where Earth's magnetic shielding is weakest. During a major solar particle event, radiation doses for passengers on a single transatlantic flight can reach levels that would trigger radiation safety protocols for nuclear workers. Nobody tells the passengers. Most flight crews don't know. The aviation industry has no mandatory monitoring system for this. Pregnant women on long-haul polar flights during solar particle events are receiving radiation doses to developing fetuses that exceed recommended limits. This is happening now, regularly, without public awareness. Number 5. Solar wind atmospheric stripping. The slow theft. The sun doesn't just radiate, it blows. Constantly, in all directions, a continuous stream of charged particles, the solar wind, flows outward from the sun at 400 to 800 kilometers per second. Earth sits in this wind permanently, has for 4.6 billion years. Our magnetic field deflects most of it. The Van Allen belts trap the particles that get through. The aurora borealis is what it looks like when that process works correctly. But the magnetic field is not perfectly efficient, and over very long timescales, the solar wind slowly strips away atmospheric particles from the top of the atmosphere, particularly light ones like hydrogen and helium. Mars shows us what happens when this protection fails. Mars once had a thick atmosphere, liquid water, possibly conditions suitable for life. Then its magnetic field died, its core cooled and solidified. Without magnetic protection, the solar wind stripped the Martian atmosphere away over hundreds of millions of years. Mars today, atmospheric pressure 1% of Earth's, surface temperature average -60 degrees, no liquid water. Earth's magnetic field is not permanent. It is generated by convection currents in the liquid iron outer core, a dynamic process that can weaken, change, and reverse. The magnetic field has reversed hundreds of times in Earth's history. During a reversal, it weakens significantly, potentially for thousands of years. During that window, the solar wind has direct access to the upper atmosphere. Number 4. Red giant expansion. The guaranteed ending. Everything so far has been probabilistic. This one is not. In approximately 5 billion years, the sun will run out of hydrogen fuel in its core. When that happens, the core contracts while the outer layers expand dramatically. The sun will swell into a red giant so large its surface will extend past the orbit of Venus, possibly past Earth's orbit entirely. If Earth survives the engulfment, and that's not guaranteed, it won't matter. The red giant sun will radiate heat so intense that Earth's surface temperature will exceed the melting point of rock. The oceans will have boiled away billions of years earlier from increasing luminosity. What remains will be a charred, airless rock orbiting a dying star. Every mountain, every ocean basin, every trace of every civilization that ever existed on this planet, gone, vaporized, or melted into the crust. The sun will then shed its outer layers and a planetary nebula, a beautiful glowing shell of ejected gas expanding outward. The ejected material will eventually be incorporated into new star systems, new planets, possibly new life. The atoms that make up your body right now will be part of that ejected material, scattered across a light year of space, eventually finding their way into new worlds. The sun doesn't end us permanently. It recycles us. Number 3. Micronovae, the threat we just discovered. In 2022, astronomers discovered something that had been hiding in plain sight in the historical record. Micronovae, smaller than a full stellar nova, but localized and devastating. When hydrogen-rich material accretes onto the surface of certain stars, it can trigger a runaway thermonuclear explosion, not across the entire stellar surface, but at one pole. A focused thermonuclear detonation on a stellar surface. The Sun is not a white dwarf, the stellar type most associated with micronovae, but the discovery revealed something important. Stars can produce explosive thermonuclear events we didn't know about until 2 years ago. What else don't we know? Solar physics is a young field studying an object 4.6 billion years old. We have been making detailed observations for roughly 150 years. We have detected activity patterns on timescales of 11 years and 22 years and possibly longer cycles of hundreds of years. We don't know what a 1,000-year solar cycle looks like at maximum. We don't know what a 10,000-year solar cycle looks like. We are drawing conclusions about a 4.6 billion-year-old star from 150 years of observation. That is less. Number 2. Superflare, the low probability extinction event. Solar flares are common. X-class flares happen several times per solar cycle. The Carrington event was large, but within the range of what our sun does. But some sun-like stars produce something far worse: superflares. Events releasing 10 to 10,000 times more energy than the largest flare our sun has ever produced. When the Kepler Space Telescope analyzed 83,000 sun-like stars, it found superflares occurring on some of them. Rarely, but occurring. If our sun produced a superflare at Carrington scale times 1,000, the ozone layer doesn't just thin, it's gone, stripped away in hours. The UV radiation reaching Earth's surface jumps by a factor of thousands. The food chain collapses from the bottom up. Phytoplankton die, plants die, everything depending on them follows. Recovery time, if recovery is even possible, would be measured in centuries. The probability in any given year is extremely low, maybe 1 in a few thousand, maybe 1 in a million. We don't have enough data to calculate it accurately for our specific star. But across billions of years of Earth's remaining habitable lifetime, low probability and long time equals eventual certainty. Number 1. The sun simply stops being compatible with life, the ending already underway. Here's the one that keeps solar physicists quiet at night. There is no dramatic ending required, no superflare, no red giant expansion, no CME. The sun is slowly and continuously changing, getting brighter, getting more energetic, cycling through magnetic activity patterns we don't fully understand, on timescales we haven't fully mapped. The window of habitability Earth sits in right now, the precise combination of solar output, magnetic activity, UV levels, and particle flux that allows complex life to exist, is not a permanent feature of the solar system. It is a phase, a window, one that opened roughly 500 million years ago when complex animal life emerged, and one that will close not with a dramatic explosion, but with a slow, relentless drift outside the parameters life requires. The sun doesn't need to explode to end us. It just needs to keep doing what it's already doing, getting slightly brighter every 100 million years, every million years, every year. The star that created every atom in your body is the same star that will make this planet uninhabitable, not through malice, not through catastrophe, just through the completely indifferent physics of stellar evolution playing out on timescales that make human civilization look like a single frame in a billion-year film. We exist in a window, and windows close. Subscribe, drop a comment. Which one actually scared you the most? See you in the next one on Cosmic Hives.